Hello friends, today we are going to be looking at a new exposition under the previous exposition worked on, which is Surd. Now, in the previous exposition, we are made to understand that Surd is a mathematical concept that deals with various irrational numbers. Now, what are irrational numbers? Irrational numbers and numbers that can be expressed in a simple fractional format. Now, we're made to understand that irrational numbers could come in different formats. For example, pi is an irrational number because pi is 3.142 and so on and so forth. So for irrational numbers, you can't just get an end to the set of decimals. So most times we end up with recurring decimals. And also set of numbers like square root of 5, square root of 7, square root of all this set of non-perfect squares, they all give us irrational numbers. So also in the previous association, we are made to understand that some set of great mathematicians, such as the Polish mathematician known as Rudolf. Rudolf did a great work. He brought about the modernization of sword, and also some Spanish Muslim mathematicians such as Al-Azan and Al-Khalasadi did great jobs also. So today we're going to be looking at the conversions between pure Surds and mixed Surds. So before we go into this, I'll love you to go through the previous association for you to understand this 100%. So how do you simplify this very pure Surd, raised to the 5? How do you simplify it and leave it a mixed Surd? Now, most times you'll be told to think of two set of numbers that you're going to multiply that will give you 7/5. So the two set of numbers, one has to be rational in nature and the other one has to be rational in nature. So that may be quite stressful because it's not going to be easy thinking of two set of numbers that one will be irrational and the other one will be rational. So there's a better way to go about it. This is a better method. Now, first of all, you're going to express this as a product of its prime factor, the way we were taught how to get the square root of numbers, one of the methods we use. So you're going to be using the tabular method. So think of all the numbers that could break this down, all the prime numbers that could break this down. So you have numbers like 2, 3, 5, 7, 11, and so on and so forth. So you're going to be breaking this down first. So you're going to look at this. Can 2 go in this? No. Can 3 go? Yes. 7 plus 5 is 12. 3 can go in it. 3 in this is 2. Remember 1, 3 here, 5. 3 can go again. Can 5 go? Surely. 5 in 25 is 5. 5 in 5 is 1. So we're done with that. So square root of 7/5 will leave us with this 3 times 5 times 5. Don't forget that when we talk about square root, we're talking about two identical set of digits. So 5 and 5 are the same. We're going to pick one of them. We pick 1, 5. Now 3 here does not have a partner, so it means that the 3 will remain in the root. So that's going to be root 3 times ordinary 5. That will give us, root 3 times ordinary 5 will give us 5 root 3. So this is very easier. It's far easier than thinking of 3 times 25. 25 is a rational number, square root of 25, while 3 is a rational number. So imagine if this figure is very big, that will be very, very stressful for us to think of. So this is a very simple way to convert root 5 to a mixed Surd. So this is 5 root 3, which is our final answer. Okay, let's see another example. This example 2. Simplify square root of 5760, 5760. Now, how do you simplify this? Now, as I said in the very first example, that most times you'll be asked to think of two numbers whereby one of them will give you, one of them will be a rational number, I beg your pardon, and the other one will be an irrational number. That very method is stressful. Now, imagine how big this very figure is. 5760, that's a pure Surd. Now, what are the two set of numbers you're going to multiply that when you multiply them, one of them will be rational and the other will be rational. That will be a very tall order. That will be very stressful. So the best way to go about this is the same way we went about the first one. So we're going to get the product of the prime factors in the tabular method. So we rule this out. This 5760. Get the product of the prime factors. You're going to be using the tabular method. So you're going to be using all the set of prime numbers right up there. 2, 3, 5, 7, 11. One after the other to test each of these numbers. So can 2 go in this? Surely 2 can go in this. You put your 2 here. 2 in 5 is 2, 4, remainder 1. 2 in 17 is 8, 16, remainder 1. 2 in 16 is 8. 2 in 0 is 0. So we're done with that. The next we use 2 can go again. 2 in 3 is 1. 2 in 8 is 4. 2 in 8, 4. We use one of these methods in our previous association when we worked on square root of numbers. So you could go through that to understand this. So next we keep using 2 until we get 1. 2 again. 1, remainder 1. 2 in 14, 7. 2 in 4, 2. 2 in 0, 0. So keep using your 2. Just continue with that. 2 in 7 is 3, 6, remainder 1. 2 in 12 is 2 in 7 is 3, remainder 1. 2 in 12 is 6, 2 in 0 is 0. 2 could go again. 2 in 3 is 1, remember 1. 2 in 16 is 8. 2 in 0 is 0. 2 again. 2 in this is 9, 0. 2 could keep walking, keep using 2. 2 in this. 2 in 9 is 4, 8, remember 1. 2 in 10 is 5. 2 can't go anymore, so we use our 3. 3 is the next thing we do. So 3 in 4, 1, remember 1. 3 in this is 5. 3 again. 3 in 5 is 5. 5 in 5 is 1. Wow, look at what we got. We've got something very big and long. So the next thing we do now is, since the square root, we're going to pick two numbers that are the same. Two equal numbers will be, we pick two equal numbers. Out of two equal numbers, we pick one. So 2 and 2, just 1. 2 and 2, 1 digit. 2 and 2, 1. Now that's two partners. You just pick one representing them. 3 and 3, you pick one. So 2 and 5, they've got no partners. So the next thing we're going to work on now, we write this out. 5760 would be all this right here. As you can see, we have a 2 times 2, 1, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 3, 3, and 5. So pick 2 already. This 2, 2, 2, and then 3. So 2 times 2. So we have this already, 2, 2, 2, and 3. So 2 times 2 is 4. 4 times 2, 8. 8 times 3 is 24. There's 24 times. So what do we have? The ones without partners, we have the 2 and 5. They remain in the root. 2 times 5. So this 24 times root 10. This 24 root 10. Okay, now here's the third question. Write 15 root 3 as a pure surd. Now don't forget the first two examples we worked on. We worked on how we could convert our pure surd to mixed surd. So right now here we have a mixed surd to be converted back to pure surd. Now it's very simple, just like converting 24 root 10, back to what we call the pure surd. So how do we do this? This 15 root 3. Now this first thing you're going to work on, 15 root 3. We give us, don't forget that this very rational number, we're going to we'll do something like this, 15 times 15. 15 and 15, you can pick one. Then we extend, we bring in the 3 that has no partner. Now this 2 here with partners, we could easily pick one of them out. So this one does not have a partner, remains in the root. So 15 root 3 is 15 times 15, which is that's the rational number becomes doubled, then times the irrational that stays single. This one's with partner naturally comes out of the root, while this one's without partner stays in the root, just like what we explained up there. So 15 times 15 is 225 times 3. 225 times 3, 3 times 5, 15, 5, keep your 1. 3 times 2 is 6 plus 1, 7. 3 times 2 is 6. So here we have it, square root of 605. This is a pure surd. So after all we've discussed today, it's high time we looked at a couple of take-homes. I'm very sure that after all we've discussed today, we could handle these two set of questions. So the first is simplify square root of 1944, that's 1944. Simplify the very stuff and leave it in mixed sort for me. So the next question is write 11 root 5 as a pure surd. So I'd love you to leave this, your answers to these two questions in the comment section for me. So we're going to be drawing the continent to today's exposition. So if you have found this resourceful, please subscribe to this very channel and share this exposition. Thanks.